Okay, chemistry kids, today we're going to be doing lesson number 1 in nuclear chemistry. So we're looking at visible learning objective 2-5, which is about the chemical reactions that take place within the nucleus of an atom. So we're talking about changes in protons and neutrons. And so we're going to do this in 2 parts. Our first lesson is going to be on types of radiation and different types of reactions that take place within the nucleus. And then the second part will be devoted to a concept called half-life. Okay, so this is lesson 1, so we're going to talk about different types of radiation. And really, we want to know how to balance and interpret different types of nuclear equations. Okay, so just real quick, let's go ahead and check the VLOs that this corresponds to. Oops. All right. So again, we're in 2-5 nuclear chemistry, and we're going to be doing 2-5 1 through 8, essentially. We'll do a separate lesson later on about half-life, so 9 and 10. But right now, today's lesson, we're going to be covering 1 through 8. Okay. So there's some guided notes that go along with this PowerPoint, so feel free to fill those in if you have a copy of those. But if not, just pay attention, and you can always come back and watch this again if you need to reference. Okay. So let's talk about nuclear chemistry. Again, nuclear just means nucleus, and so we're talking about changes that involve the nucleus. So when we say a nuclear reaction, that's a nucleus change. Something's going on with the nucleus, okay? And if something happens to the nucleus, especially if something happens to the number of protons, right, the element changes, okay? So what's the difference between chemical reactions versus nuclear reactions? Chemical involves the electrons. A chemical change is really just the exchanging or sharing of electrons. And when it comes down to chemical reactions, those are the reactions we're used to seeing on an everyday basis because when atoms bump into each other, it's what's on the outside that actually come in contact. The nuclei don't really come in contact, okay? So when we're talking about nuclear reactions, we're talking about things that either take place spontaneously because a nucleus is just trying to become more stable. But if we talk about fusion, which is smashing nuclei together, it takes a tremendous amount of energy for that to happen. So it doesn't really happen every day, here on Earth. It does happen every day in our sun, but naturally when we think reactions, we think chemical reactions. We don't really focus on nuclear reactions in chemistry. So this is the one time where we're really going to focus in on what's going on with the nucleus, okay? So nuclear involves the nucleus. So we're talking about protons, neutrons, and stuff like that, all right? So when does the nucleus change? Okay, so the nucleus has the protons and neutrons, and there needs to be a stable ratio of protons to neutrons for the nucleus to be considered stable. And if you look at the heavier elements on your periodic table, as you look at them, you start to notice that there becomes a lot more neutrons than protons. If you look at the lighter elements, most of the common isotopes of the lighter elements, it's like same number of protons, same number of neutrons. If you look at carbon, the most abundant isotope of carbon is carbon-12. It's atomic number 6, so that means 6 protons, 6 neutrons. The most abundant isotope of oxygen is oxygen-16. It has 8 protons, so that means it's got 8 neutrons as well. So a lot of times there's this 1-to-1 ratio of protons to neutrons, but as you get heavier and heavier elements, you start getting a lot more neutrons than protons. And so there are different ratios of protons to neutrons which are stable, but then there's ratios that are unstable. And the more unstable the nucleus is, the more it spontaneously will try to change, okay? So you don't need to know the belt stability, and you don't need to know the ratio of neutrons to protons, which ratios are stable and which ratios aren't. Just understand, once we get above atomic number 82, which is lead, pretty much all those nuclei all those atoms past lead on the periodic table are not very stable when it comes to radioactive decay. So those very heavy elements, especially those ones down there at the bottom of the periodic table, where you see elements like uranium, maybe you've heard of uranium, maybe you've heard of nuclear power plants using uranium as their nuclear fuel. And now we really kind of want to talk about what's going on there, okay? So you don't need to know the belt of stability, but understand, over here I have kind of one, this symbol right here is beta, and this symbol right here is alpha. And it really just depends on what your neutron to proton ratio is. That's going to determine what type of radioactive decay you have. So later on this lesson, we're going to learn about what beta decay is. We're also going to learn about what alpha decay is, and whether a nucleus is going to undergo alpha decay versus beta decay really depends on the number of, or the ratio of neutrons to protons that you're starting with, okay? So the two types of nuclear change, the nuclear reactions, are nuclear fission, which we're going to be talking about in depth today. It's where a bigger nucleus breaks up into smaller nuclei, okay? So a big atom is breaking up into smaller atoms. And then we also have nuclear fusion. And nuclear fusion is where you're taking smaller atoms and you're forcing the nuclei together. So you're building the nucleus up in fusion, okay? In case you're wondering, the nuclear power that we use in nuclear power plants is nuclear fission, although there have been some recent breakthroughs in nuclear fusion. If you can crack the code of fusion and get that working for us, it's going to be clean energy, and it's going to be the only waste is helium, and we're running out of helium, so that's pretty nice. And it's going to be not only would it be clean, it would could theoretically produce a lot more energy than the fission reactions we use. So figure that out, become a trillionaire, and win that Nobel Peace Prize. Okay. I'm just going to skip this for now. This is not really something that you need to know, but we'll if when you come back to class, we can talk about mass defect. Okay. But right now, let's talk about the different types of radiation. Okay. So when we say an element undergoes decay, radioactive decay, it means the nucleus is emitting one or more of these types of particles, all right? So the types of radioactive decay, the types of radiation emitted by the nucleus can be the following types. So you have alpha particles, which essentially is just a helium nucleus. So it would be, an alpha particle is just 2 protons and 2 neutrons, and they're being ejected from the nucleus to try to stabilize the nucleus, right? So, but because it's only protons and neutrons, and it's not helium, the atom, it's just the nucleus of helium, it would have a 2+ charge because there's no electrons associated with it. So it's protons, 2 protons, 2 neutrons being ejected from the nucleus. Alpha particles are the kind of biggest type of radiation, but they have the least penetrating power. They sometimes can penetrate, depending on how thick the paper is, they could penetrate paper, but they're not going to be able to penetrate, through multiple sheets of paper or anything like that. So if you have alpha particles being, shot your direction, you can stop it with your clothing. It's not a big deal. All right. Then you have beta. Now, technically, there are 2 types of beta particles: beta negative and beta positive. We're gonna say beta particles when we refer to beta particles, we're only going to refer to beta negative, which is essentially an electron. So this is the symbol for a beta particle, right? Which looks like our symbol for an electron. It has a charge of -1. Okay. And beta positive, instead of calling it beta positive and beta negative, we're going to call it beta particle and electron. And we're going to call the positive one, we're going to call a positron. So you'll notice that the difference between a beta particle and a positron is the beta particle is negatively charged and the positron is, the beta particle is negatively charged and the positron is positively charged. These are opposites of each other, What a positron is the antimatter electron. So electron is the matter, and the antimatter form of an electron is a positron. Okay. So we have alpha particles, we got beta particles, we got positrons that can be emitted from the nucleus, and then we also have gamma radiation. Now, gamma has this symbol here. It kind of looks like a Y, but it doesn't have a mass. It doesn't have a charge. It's just very high energy light. In fact, gamma radiation has the highest energy, and it has the most penetrating power. If you've ever had an X-ray, which is also high energy light, gamma radiation is even higher energy than X-rays. But if you've ever had X-rays, which are high energy light, you always get a lead kind of blanket to put over your private area to protect your private area from those high energy light waves. So gamma is the most dangerous type of radiation there is, but it does the least. It doesn't change the nucleus. The nucleus. It doesn't change if gamma radiation is released by the radioactive element. The gamma rays don't change the nucleus of the element in terms of mass and charge. Okay. But these are the types of different things. So if I say something undergoes alpha decay, it means it loses one of these particles. If I say something undergoes beta decay, that means it loses one of these particles. If it emits a positron, that means it's losing one of these particles. And then it could also be losing gamma or releasing gamma radiation, but there is no change to the nucleus of gamma radiation is released. Okay. So let's look at nuclear decay here. So if I say uranium-238 undergoes alpha decay, we're saying uranium-238, and this is how you write a nuclear equation. So you would write uranium-238 yields, and then an alpha particle, right? Alpha decay means it lost an alpha particle. So on the other side of the yield sign, we would put the alpha particle, and mass number goes on top, atomic number goes on bottom. And so if this is 4 and this is 2, and you can think of the arrow as an equal sign, then what number would have to go here? Well, these two numbers would have to add up to that number. So if you know that number is 238, because you were told in the question, or right at the beginning here, that's 238, and that's a mass of 4, then the missing mass here is 234. And then again, if this is 92, and this number's 2, because we knew it was an alpha particle, then the missing number here is 90. Now, how do we get that chemical symbol? Well, we go to our periodic table, and you go to atomic number 90, and it's thorium, Th. Okay? So this would be a balanced chemical, or not really chemical. This would be a balanced nuclear equation that shows the alpha decay of uranium-238. Okay. So one thing to just understand, if the nucleus releases an alpha particle, your mass number is going to decrease by 4, and your atomic number is going to decrease by 2, because you're losing 2 protons, so your atomic number is going to go down by 2. But you're also losing 2 neutrons. That's a total of 4 AMUs you're losing, so your mass is going to go down by 4. All right, so if we look at, again, notice if uranium-238 undergoes alpha decay, alpha means my mass goes down by 4, and that's what happened, right? 238 to 234. And my atomic number goes down by 2, 92 to 90. Okay? Okay, so beta decay or beta emission here, if something undergoes beta decay, all right, there's our beta particle. So iodine-131 undergoes beta decay. So here we go. This number's 131, yields a beta particle, and that number's 0. So notice the mass doesn't change. So when something releases a beta particle, the mass doesn't change. But notice the atomic number increased by 1. And again, if you treat this like an equal sign, it would be 53 equals 54 plus a negative, or sorry, 53 equals x plus a negative 1. So that x must be 54. Okay, so when you get a beta particle released, which again is just an electron, Your mass doesn't change, but your atomic number actually increases. Okay? And then if you look at a positron instead of a beta particle, so if you look at a positron, if something undergoes positron emission, notice that the mass stays the same, but the atomic number decreases by 1. Okay, and again, this is all about getting more stability, right? This is all about gaining more stability of the neutron and proton ratio in the nucleus. So something's got to change within that ratio, all right, to become a more stable nucleus. Okay, so maybe when I said an electron gets ejected from the nucleus, maybe that threw up a red flag for some of you. And it probably should have, because we just spent the entire first part of this unit talking about the electrons that are on the outside, the electrons on the outside, the electrons on the outside. And that's the truth. Okay, so there are no electrons in the nucleus. But neutrons and protons are pretty cool in that in order to gain that stable ratio of neutrons to protons, neutrons can actually split into a proton and an electron. And here is that nuclear equation. So a neutron can turn itself into a proton, okay, and it emits the negative charge, which would be the electron. So the proton, as the neutron turns into the proton stays in the nucleus. And so that's why the mass didn't change. It doesn't matter if if a neutron turns into a proton, the mass doesn't change, okay? But the overall charge of the nucleus would increase by 1 because you've gained a proton. And that negative charge, that splits off, is the beta particle. That is the electron that gets ejected from the nucleus and flies out as the radioactive particle. Okay? So it's pretty neat. One way to think of a neutron, even though it's not really necessarily the correct way, but you could think of a neutron as the combination of a proton and an electron. Because in nuclear reactions, it goes this way. The neutron actually can split into a proton and a beta particle, an electron. Okay. So how does a positron form? Well, that's the opposite. That's where a proton in the nucleus can turn into a neutron and get rid of its positive charge. Essentially, it's shedding the positive charge. So the proton gets rid of its positive charge, not the mass though. The mass stays in the nucleus as a neutron. It just gets rid of that positive charge, ejects that positive charge out of the nucleus, and you got positrons. Okay. Okay. So what about gamma radiation? Gamma radiation, you just need to know, is really high energy light. It's the most penetrating of all the radiation. And if you're going to be handling something that is emitting gamma waves, you want to know about it so you can protect yourself and wear the right clothing to protect yourself. Probably lead-based shields and things like that. So it's definitely important to know about. Okay. So again, just basic definitions. If you have alpha decay, you're losing an alpha particle. If you have beta decay, you're losing a beta particle. And if you have positron emission or whatever, you're losing a positron. And remember, how does a beta particle form? The neutron splits into a proton and the beta particle. How does a positron form? The proton splits into a neutron and a positron. Okay, and you might see all these different words down here: eject, decay, emit, lost. That means put whatever particle we're talking about, alpha, beta, or positron, put that on the right side of the nuclear equation. And I'm going to show you on the whiteboard here in a second what I mean by that. But that means they're products. That means these particles are products of your nuclear equation. Okay, and then just know the word transmutation does mean an atom of one element turning into an atom of a different element. Okay. So you can have fusion, right? So you can add things to the nucleus. And so a lot of times we call it capture or bombardment. When we bombard something, neutron bombardment, you're throwing neutrons at the nucleus, hopefully the nucleus will capture neutron, or you can have beta capture where a beta particle is captured by the nucleus. Okay, and whenever you see those words, unlike the eject, decay, emit, okay, if something is emitted from the nucleus, it's going to go on the right side of the equation. But if something's captured by the nucleus or bombarded into the nucleus, it's going to be on the left side. So notice this was beta capture. If this had said beta decay, this particle should be on that side of the equation. But since it was beta capture, we're adding the beta particle to the silver nucleus here. So they're on the same side of the equation, okay? And so again, you just do the math. You get, so if this is 106 plus 0, that means this number has to be 106, and this would be 47 plus a -1, so that's 46. How do I know this is palladium? Well, I go to my periodic table, I look at number 46, it's palladium, and I'm good to go. Okay? All right. So neutron bombardment of uranium-235, that would mean I would take a uranium-235 atom, and instead of, it's not neutron decay, it's neutron bombardment. So I'm adding a neutron to the nucleus. So if you look at the at this reaction, we're adding the neutron to that nucleus. And again, we just do the math. So we're taking uranium-235 and we're turning it into uranium-236 to maybe improve that neutron to proton ratio, or to actually make the nucleus a little bit more unstable to kickstart a chain reaction. And that's really the reaction that happens inside some nuclear power plants that use uranium as their nuclear fuel. Okay. And then you can have nuclear equations where you have, more than, a few different types of decay. I'll show you how to do that equation, but this is what the answer would be. Okay. And again, right, here's kind of a chain reaction picture of what's going on. A uranium-235 gets bombarded by a neutron that turns it into uranium-236, which is really unstable, and then it immediately splits into barium and krypton. And when that happens, it releases 3 more neutrons, and those 3 more neutrons can then go bombard other uranium-235 atoms to cause this same reaction. And notice gamma rays, high energy light is produced. And that's really what's going on in the power plant. And we can talk more in detail in class about that. It's not really something that you need to know. But I just want to show you a couple things on the board on how to balance nuclear equations. And then that'll be it for this lesson. And then we'll focus on half-life for the next lesson. All right, so let me switch my camera. I think, can I?